So next, we are going to discuss the single-stage multi-machine systems. Single-stage multi-machine systems are a special case of flexible manufacturing systems. The machining centers in single-stage multi-machine systems are identical and versatile, so that all operations on any part can be performed on any one machine. Once a part is loaded on a machine, it does not leave the machine until all required operations are performed. Under this type of manufacturing system, the tool delivery system becomes the critical resource. So in figure 3, we have a tool delivery system in a single-stage multi-machine system. And this is a system with a centralized tool storage. And we have several machine setters, a total of 8. And those are the MC1, MC2, MC3 up to MC8. We have those gray parts here. Those are the tool magazines. And we have a tool area right here. This is the cell tool chain where the tools are stored. And then we have this carrier which moves the tools to the different stations or the different machine centers as needed. So on the other side, what we have is the input-output buffer with an RGB that it is used to transport the parts to the machines. So those gray squares are those representing the parts. So we have these RGB moving parts to or delivering parts to each one of the machine centers. And as mentioned on the previous slide, the tool delivery system is our critical resource. So the tools are being moved between machine centers where they are needed, and that is the critical resource under this delivery system. In figure 4, we have a tool delivery system in a single-stage multi-machine system. So this is a system with a distributed tool storage. So here's the central tool storage area. And we have the tool carrier right here, which is moving around the system and delivering those tools as needed. And here we have the load and unload station for the parts. So the parts are going to be moving into the stations using this part transporter. And they are going to be assigned. So like here, that part is assigned to that particular machine. So parts are moving in this area, and the tools are moving on the outside. So this is a system with a distributed tool storage. So in terms of the parts arrive according to the production requirements schedule. A part transporter system handles the delivery of parts from the input station to the machine and from the machine to the output station. A part cannot be processed unless the required tool is available. In terms of the tools, the required tools are specified by the process plan. Some tools are resident to the machine, while others are stored in a centralized tool storage system. The part transporter The part transportation activity is minimal since a part visits a machine only once. Vehicles are dispatched based on the parts arrivals and also based on the job completions. When vehicles are idle or when vehicles become idle, with one or more parts waiting to be transported. A tool carrier handles the transport of tools to and from the centralized tool storage and the machines requiring the tool. One can also reallocate the tools when opportunities arise. So in this figure, figure 5 shows a combined schedule of machines and tools. So at the top, we have the schedule for two machines, machine 1 and machine 2. And then these T1, T2 basically are representing the tools that are assigned to each one of the machines. So for example, machine 1 will have tool number 2 up to time 5, and then tool number 3 until time 1, 2, 3, 13, and then tool number 2 again, and then M2 will have a different schedule. And you can see that those schedules should match the activity for the tools. So in this case, we have 3 tools. So as we saw here, tool 1 will be in machine 2, which is corresponding to this box. And then tool 1 is going to be also in machine 2, which is corresponding to this box. So you see that the schedule is different for the tool and the machine because we have 3 tools, and also because the requirements for the jobs that are going to be processed will be different. So the machines will be asking for different set of tools according to the arrivals of the jobs for that specific schedule. But you can see that there's correspondence and for the machine schedule and also for the tool schedule when you compare them. Just-in-time manufacturing. The just-in-time production system was developed more than 4 decades ago by Ono Taichi at the Toyota Motor Company in Japan. Just-in-time applies to all forms of manufacturing. And in this manufacturing technique, they divide waste into the following 7 categories. And the goal of the just-in-time manufacturing is to minimize the waste. So that's why they have a classification for the different type of waste in the manufacturing flow. So the first type of waste is the waste arising from overproduction. So when you think about waste, you think about something that needs to be thrown out. In this case, is waste in terms of something that is not generating a benefit for the company. So if you overproduce and you're not selling those parts, then you need to spend money like in warehouses, for example, in order for putting that overproduction until you can move that overproduction. So that's why they see it as a waste. You don't want to have to invest in having a building for a warehouse if you don't need it, if you don't really need it. So overproduction is something that they see as a waste. Waste arising from time on hand. So if you have things like work in process in your manufacturing floor that is not being moved, it's not being processed, that's the type of waste. Waste arising from transporting. So you want to minimize the transportation of parts, and that's why this is connected to facilities planning. So our layout has to be efficient so we can minimize this waste. Waste arising from processing itself. So are you using the best, do you have your employees trained in a way that they can process parts and the product efficiently? So you don't spend more time than you have to. Waste arising from unnecessary stock on hand. So you ordering parts or yes, are you ordering more parts that you need to? Sometimes that this is something that you will see, like if you have a supplier, sometimes they're gonna give you a better price if you order a larger amount of parts. So so do you want to have that stock on hand? Again, if you buy more than you need, you're not gonna use those parts, so you have to find a place to put those parts until you need them. So there's a waste in terms of the cost of additional space for storing items. Waste arising from unnecessary motion, and this is more connected to the design of the workstation for your employees. So you want to make sure that you provide an area in which they know what they need to do and they don't are not wasting time or wasting energy in things that they don't have to do, like reaching for parts that are too far away, or walking to areas that they to find or to ask questions. So you want to provide the information, the parts, and everything that is needed for your employees to do the work. Waste arising for producing defective goods. So this is a very important one. You want to make sure that you are producing parts or producing a product that has high quality and has a high reliability. So waste arising for overproduction, result of a production philosophy based on achieving economies of scale. That is, as the production lot increases, the unit production cost will decrease. So Ono, the person that came up with just in time, states that production line must be reorganized, rules must be established to prevent overproduction, and restraint against overproduction must become a built-in feature of any equipment within the workplace. So that's what just-in-time is trying to do. Waste from time on hand arises when a worker tends only one machine. Assigning more machines per worker will reduce this waste. A better layout may also contribute to maximizing the number of machines that one worker can tend. So if you remember our discussion on cell manufacturing, so in those cells, you can have a person taking care of multiple stations. This has resulted in workers with multifunctional skills. Waste from transporting comes from moving items over long distances, from work in process storage, and from arranging and rearranging parts in containers and or pallets. Waste from transporting can be eliminated if the machines are placed close to each other, and which is something that we also discussed in a previous lecture. Waste from processing. An operator is unnecessarily tied up on a machine due to poor workplace design. For example, a pneumatic clamping device to hold work parts allow an operator to do more productive work. Waste just-in-time philosophy is implemented. Visibility can be obtained by the following technique: electronic boards for quick feedback, pull system with canvas, problem boards, and color standards. So if you want to see an example in a video on how this pull system works with Canvas, there's a link here. You can click on this link and it will take you to a very short video on YouTube that shows you the idea behind the pull system with Canvas. And containers, decentralized storage systems, marked dedicated area for inventory and tools and so on. Simplicity can be achieved with a pull system with Canvas. Simple setup changes, certified processes, small lot sizes, level production, simple machines, simple material handling, multifunctional workers, teamwork, etc. Waste Just-in-time philosophy is implemented. Flexibility can be achieved with short setup times, short production times, small lot sizes, Kanban cards, flexible material handling equipment, multifunctional employees, mixed model sequencing lines, etc. Standardization can be achieved with standard tools, equipment, pallets, methods, containers, boxes, materials, and processes. Organization is required for setup, for cleanliness, for work areas, for the Kanban system, for the storage area, for tools, for teamwork activities, and more. The impact of just-in-time on facility design. There are many concepts and techniques related to the just-in-time production system that impact building design, facility layout, and the material handling system, such as the reduction of inventories, deliveries to points of use, the quality at the source, better communication, line balancing, and multifunctional workers. In terms of reduction of inventories, inventories can be reduced if products are produced, purchased, and delivered in small lots. If production schedule is level appropriately. Quality control procedures are improved if production, material handling, and transportation equipment are maintained. Products are pulled when needed and in quantities needed. If inventories can be reduced, space requirements are also reduced. So you don't need to have a big facility or a large, you will need just the space that is required for your facility. Smaller loads are moved and stored, justifying the use of material handling and storage equipment alternatives for smaller loads. And storage requirements are reduced, justifying the use of smaller and simpler storage systems and the reduction of material handling. Consequently, the building could be smaller, a better plant layout could be used, and fewer handling and storage requirements might be needed. In terms of deliveries to points of use, if products are purchased and produced in smaller lots, they should be delivered to the points of use to avoid stockouts at the consuming processes. Quality at the source, every supplying process must be regarded the next consuming process and the ultimate customer, and each consuming process must always be able to rely on receiving only good parts from its suppliers. To achieve the quality at the source concept, the following could be required. Proper packaging, stacking, and wrapping procedures for parts and boxes on pallets and containers. Efficient transportation, handling, and storage of parts. A production system that allows the worker to perform his or her operation without time pressure. And that's the last slide for this lecture. So in this lecture, we discussed the fixed automation systems. We discussed different types of manufacturing systems, including the fixed automation system, flexible manufacturing systems, the single-stage multi-machine systems, and just-in-time manufacturing.